All right, math nerds and other assorted birds, we're going to learn a little about topology. And on we go. So a subset of the reals specifically, is called open if it has the following property. For any element of the set X, there is a positive number epsilon, so that the interval from x minus epsilon to x plus epsilon is a subset of A. Every point in the set must admit some positive number so that that little interval fits within the set. Note that the epsilon has to exist based on x. It does not have to be the same epsilon for every x. So no matter where you are in the set, think of this as a distance, okay? Epsilon is a distance you can move to the left and to the right and still be in the set. So for example, if here is our real number line, and I were to take something like this set right here. Okay, so now pretend you take a point in this set. It could be this point right here. Does there exist a positive epsilon so that everything to the left and right is still in this set? Sure. This distance here, okay, if this is x and here is my x minus epsilon to x plus epsilon, everything within distance epsilon of that point x is still in the set. What about this point right here? If I call this x, yeah, I can put a tinier little bit around it and go from x minus epsilon to x plus epsilon. So if you can do this at every point in the set, you're what's called an open set. So as an example of something that isn't open, okay, just imagine the single point, I don't know, 12. So the set is just one point and it's 12. If I pick a point in the set, I don't have much option, it's got to just be the point 12. I cannot put any positive distance left or right and still be a subset of the set. No matter how far I move to the left or right, no matter how small, I'm going to leave the set that just contains the number 12. So sets are called open in a sense because you are open to move around in them. Okay? At any point in the set, you have some freedom of movement in all directions. Now, there's another definition called closed. A set is called closed if its complement is open. Note that this is not the same thing as saying the set isn't open. No, a set is called closed if its complement is open. So this is not much of a definition so far. It's a little weird, in fact, to say a set is called closed if something is true about its complement. So why would we define it this way? We'll see. There's an equivalent definition later on, but this is a simple way to get introduced to the term. Okay, so here's a theorem. If I make an interval where I do not include the endpoints, that is always an open set. And yeah, we call them open intervals, but we call them open intervals because they are open sets. They are not open sets because we call them open intervals. So let's take the example where the left side is actually minus infinity and the top is a real number, although all cases would be treated more or less the same way. So we have the interval from minus infinity to b, not including b. What we need to show is that no matter where we start in this interval, there is some epsilon, so that this interval is a subset of that, so that everywhere epsilon to the left and to the right of x is still in the interval we started with. So pick any x in the interval. So x is an arbitrary real number in between minus infinity, which is a tautology, and b. So it's a real number, and therefore b minus x is positive because x was less than b. If I subtract x from both sides, b minus x is a positive number. That's going to be our epsilon. So x minus b minus x to x plus b minus x is all going to be in the interval from minus infinity to b. So let's prove that. Pick anything in between x minus epsilon and x plus epsilon, let's call it y. It must therefore be less than x plus epsilon because it is in the interval that ends at x plus epsilon. Since epsilon is b minus x, if I just replace or substitute this epsilon for this one, we get exactly that y is less than b. And if y is less than b, it belongs to the interval of that form, minus infinity to b. So any y less than x plus epsilon will in fact be less than b. So here are a couple of sample problems for you to do. The first one is of particular note. That set is not open and it's not closed. A common mistake is to think that a set must be either open or closed, so if it's not one, it is the other. Not the case. So go ahead and pause here and work through these problems. Now, one thing, if you paused and worked through, note that the real numbers are an open set, and therefore by definition its complement, which is empty, is closed, but you can also prove that the empty set is open, and therefore its complement, which is all the real numbers, is closed. So the real numbers and the empty set are both open and closed. Okay? It is possible for a set to be open and closed. The notions of what sets are open plays very nicely with intersections and unions. So for example, if A and B are both open sets, then so is their union. So for example, here is our real number line. Maybe this is my set A, and this is my set B. They're both open intervals. When we draw sets, we tend to default to intervals, but remember, they don't have to be intervals. And in fact, A union B is not an interval. It's this set together with this one. However, if you were to pick any point in that set that you wanted, it would either be over here, and since A is open, I know that it will admit a little interval around it, or it might be over in B, and therefore since B is open, it will admit a little interval around it. Whether you belong to A or you belong to B, either way there's going to be some wiggle room. And that's basically the proof, but let's go ahead and do it formally. Let x be an element of either A or B. It's in the union. If x is in A, since A is open, I know that there is a little interval, x minus epsilon to x plus epsilon, that's a subset of A. But if it's a subset of A, it's a subset of A union B. Similarly, if x is an element of B, there is another epsilon because B is an open set. It might not be the same epsilon. Remember, this epsilon can change, but there's always some positive number at every point because A and B individually were open sets. Now work through some similar problems. Note that some of these unions and intersections are infinite and some of them are finite. Now, did you work through these problems? I sure hope so. The observation to make here is that unions of any number of open sets, finite or infinite, are still open, but not necessarily infinite intersections of open sets. That wasn't actually assigned here, but infinite intersections of closed sets will still be closed, but not necessarily infinite unions. So yeah, unions can undergo open sets can undergo infinite unions. Closed sets can undergo infinite intersections. And that is in fact really just De Morgan's law. In fact, if you had proved the first two successfully, then you can probably prove the second two just by applying De Morgan's laws. And now a new definition, a limit point. Suppose we have a set A, some subset of the reals, and another number x, maybe it's an A, maybe it's not, that wasn't declared. We're going to call it a limit point of A if every open set containing x intersects with A non-trivially, non-empty. So if x is in an open set U, then that set U must intersect A. So imagine here is our real number line, and here is a set. It's an interval which contains one endpoint but not the other. One thing to point out is that everything in this interval is a limit point. So pick something in the interval like this. If I call this x, okay? Now imagine I have an open set U, and x is an element of it. Well then, I can put a little interval, x minus epsilon to x plus epsilon, and still have that be a subset of U. So maybe it's like this. But notice that this set now must intersect A non-trivially. How do I know it doesn't intersect A with the empty set? Well, X is an element of both. If X is an element of A, then if it's an element of an open set, that open set must intersect A. So that takes care of everything in the interval. Everything in the interval is a limit point because anything in a set is always a limit point of that set. But what about this endpoint right here? Okay, so let's pretend this is the interval from -2 to 6. What about -2 itself? I claim -2 is a limit point of this interval even though it is not in the interval. So suppose -2 belongs to an open set U. Well then, since this is an element of U which is open, I must be able to form an interval of the following form and have that be a subset of U. But therefore, this contains some x's which are bigger than -2, because it goes all the way up to -2 plus epsilon. So looking back at the original picture, if I can go all the way up to -2 plus epsilon, there will be numbers that are in between -2 and 6. So therefore, U intersect A is not empty. It doesn't matter how small this epsilon is. No matter how small it is, I'm still going to contain numbers bigger than -2, and therefore the open set U will intersect the interval. So even though -2 was not in the interval, it is a limit point of it. So the first thing we observed is that if X is an element of the set, then X is a limit point of A. That's pretty straightforward. But here's the kicker. A set is closed if and only if it is equal to the set of its limit points. We saw in the drawing that the set always has as limit points elements of the set. Everything in the set is a limit point of it, but there might be points not in the set that are still limit points of it. A set is closed when that doesn't happen, when the only limit points are actually elements of the set. Now that has to be proved. Yeah, being closed in a sense means you are not missing any of your limit points. Anything you can construct as a limit point of a set was already in the set. It is closed off under the idea of taking limit points. So the proof that the set A is closed if and only if it's equal to the set of its limit points is, well, we have to do two different things. If it has all of its limit points, then it's closed, and second, we go the other way. Now let's get to proving it. Okay, the first thing we were going to prove was that if A has all its limit points, then A is closed. So let's assume A contains all of its limit points, but we're going to assume to the contrary that A is not closed. Well, if A is not closed, its complement is not open. Remember, the definition of closed is complement is open. So if A is not closed, its complement is not open. To be open, a set has to have the property that every point in the set has a little epsilon ball around it, epsilon neighborhood, epsilon interval. Every point in the set has to contain one of these epsilon intervals. That's also a subset of what we're talking about. So if R minus A is not open, not every point does this. So there is some point, and I'll call it Y, that doesn't have the property that there is an epsilon, so that interval is a subset of the A complement. So if R minus A is not open, there is some point so that for any epsilon, Y minus epsilon to Y plus epsilon is not a subset of A complement. Well, if you're not a subset of A complement, you contain points not in A complement, and if you contain points not in A complement, you contain points in A. In other words, there's some point Y so that every interval of the form Y minus epsilon to Y plus epsilon contains points that are in A, which is exactly the definition of Y being a limit point of A. Every open set containing Y must intersect with A. That is the definition of being a limit point of A. So assuming A is not closed allowed us to find a point Y that wasn't in A. Okay, Y was not in A. That was something we assumed at the very top, but it was a limit point of A. So if A is not closed, it must be missing one of its limit points. And the contrapositive of that is if it has all its limit points, it must be closed. So the pictorial version of what we just did. So we assume A is not closed. In other words, the complement is not open. Okay, open would be for any element in the set, there exists an epsilon so that this interval is a subset of that thing. So if I negate this whole thing, we would get there exists a y in the complement of A so that for any epsilon, which is positive, the interval from y minus epsilon to y plus epsilon is not a subset of R minus A. Now, what does it mean to not be a subset of something? There exists something in this interval which is not in that set. And if you are not in R minus A, then you are in A. So there is some point not in A, so that no matter what epsilon you pick, there is something in this interval which is in A, which tells me that y is a limit point of A. That's exactly what all of this on the right shows. This point z has the property that y has the property that everything around it intersects A. Therefore, y is a limit point of A. So if R minus A is not open, in other words, if A is not closed, then there is a point that is not an A but is a limit point of A. So not being closed means you have missed one of your limit points. Now assume that A is closed. In other words, R minus A is open. Well, for any point in R minus A, in other words, for any y not in A, since the complement of A is open, I can put a little interval around it which completely misses A because the complement of A is open, so this little interval is a subset of the complement of A. And therefore, y is not a limit point of A. I was able to find some little interval, y minus epsilon to y plus epsilon, that does not contain any points of A. So imagine we assume that A is not closed. Sorry, A is closed. That's the one we're doing now. In other words, the complement is open. So if I pick any point here which isn't in A, since the complement of A is open, there must be an interval of this form that is a subset of the complement of A, because the complement of A was open. Well, if it's a subset of the complement of A, its intersection with A is empty. And therefore, y is not a limit point, because I was able to find one interval of this form that doesn't intersect A. Remember, being a limit point says every interval of that form does intersect A. So if one of them doesn't, you're not a limit point. So if A is closed, every point in the complement is not a limit point. Any point in the complement you start with cannot be a limit point of the set. Therefore, all the limit points don't belong to the complement, and if they don't belong to the complement, they belong to the set. So if no point in the complement of A can be a limit point of A, it must contain all its limit points, and we've proved both directions. A set is closed, which by definition means its complement is open, if and only if the set contains all limit points. All right, an optional topic, covers of sets. So suppose you have a collection of sets. The individual sets B sub t belong to the collection of sets, which I've called B. If A is a subset of the union of all of these things, we say that the collection B covers A. If the collection only has finitely many elements, we call it a finite cover of A. It does not mean the sets in the cover have finitely many elements. It means there are only finitely many pieces to the cover. Okay, if every element of a cover is open, we call it an open cover. So here's what we mean. I'm going to draw a two-dimensional picture. So imagine this is my set A. Now my individual sets B sub t do not have to be finite sets. Maybe this is one set B, I'll call that B1. Here is another set, call this B2. Here is a set, I'll call that B3. Here is a set, B4. Here is a set, call that B5. And then finally, let's just do a big lumpy thing like this. B6. So notice, if I fill in all of the green things, I will cover the red one. Okay, all the B's, if I fill them in, cover the A. So even though the sets B have infinitely many elements in them individually, the collection only has 6 elements. There were only 6 sets that I put into this collection. This is a finite cover of A. You can have an infinite cover of something. Imagine A to be this circle. Okay. Now, my sets B are going to be as follows. This circle, this circle, this circle. They're just getting wider and wider, and they're solid. They're filled in. I'm just not drawing it. If I imagine the circles expanding out towards the red one, all of the B's are expanding out, but never quite reaching it, then maybe it would require infinitely many B's to cover the A. Now, if I have a cover of A, and I take a collection of some of the pieces of the cover, a subset of B is not a collection of subsets of the things we started with. Okay, the B was a collection of certain sets, and now I'm only taking some of those sets. The individual sets have not changed, I'm just only including some of them. We call that a subcover. We don't get to change what the sets are in the cover except to decide which ones we keep and which ones we get rid of. Okay, so a subcover is made by taking the cover and taking some of its elements, and the elements of the subcover are themselves sets. So we take a subset of that collection of sets without having changed what those individual sets were. That is a subcover, correct. Why all this stuff about subcovers and finite covers and open covers? Well, a set is called compact. If any open cover has a finite subcover of the set A, any way you can cover A in open sets, there must be a way to do it with only finitely many. So even if you began with an incredible collection of weird and infinitely many open sets to cover up A, there would be a way to pick finitely many of them and also cover A. And yeah, this is a very abstract definition. We can define this. Okay, a set is called compact if any open cover has a finite subcover. But why would we do it? Well, we'll see later on. This is a useful definition. Okay, and I admit it's a lot weirder than other stuff, and it's hard to get your brain around at first. But it does become very useful when talking about certain other definitions of how functions behave. Okay, since we're only dealing with functions from the real numbers to the real numbers, it's basically an abstract concept, an optional concept, and it will reduce down to something simpler. A set in the real numbers is compact if and only if it is closed and bounded. Okay, so if a set is closed, in other words, its complement is open, or it contains all of its limit points, either one, they're equivalent, we showed that, and it is bounded, then it has this weird property that any cover by open sets has a finite subcover. For now, we're only going to prove part of it. If a set is compact, then it is bounded. We want to show it's closed and bounded. We're going to start by at least showing it's bounded. Okay. And yes, the term compact certainly seems to imply bounded, but that's not enough. Observe. If I take the interval from -n to n, where n goes through the positive integers, so -1 to 1, -2 to 2, -3 to 3, and so forth, if I just union all of those, I get all of the real numbers. All real numbers will eventually be in one of the intervals from -n to n. Therefore, any set A, which I assumed was compact, will be covered by this, because it covers all the real numbers. And these are all open sets. So if A is compact and I have an open cover, there must be a finite subcover. So what we have is I took the interval from -1 to 1, then the interval from -2 to 2, then the interval from -3 to 3, and so forth. Observe that these are contained within one another. So if I union this interval with this one, I really just have the interval from -2 to 2. If I then union with the interval from -3 to 3, I just have the interval from -3 to 3. So if A is any set in the reals, doesn't even matter which one, okay? It will be covered by this because these will eventually cover all the reals. But a compact set is one where an open cover has a finite subcover. So if A is compact, it's not just covered by this, it's covered by a finite collection of them. And if I have a finite collection of positive integers, there's a last one. Meaning, I can just stop there at some capital N. Remember, we noticed that if I union some of these intervals, if I take the union, for example, of -2 to +2 and -8 to +8, I really just have -8 to +8. So if I just union some of these, it's just going to be the same thing as whatever the last one was. So if I have a finite subcover, it ends at a certain capital N, meaning A must be contained in just that interval from -n to +n, which means it's bounded. Okay, so suppose my infinite cover was -1 to +1, -2 to +2, and so forth. Since A is compact, so A can be covered with finitely many. Let's suppose, just for the sake of argument, that A is covered by -2 to 2 and -6 to 6 and -10 to 10. Well, if I union all of these things here, that's just -10 to 10. And therefore A is bounded because it belongs to the interval that goes from -10 to 10. So anything which is compact in the reals must be bounded. We will eventually prove it's also closed, but it takes a lot more work, and we're not going to do it right now. So why was this called topology? Well, a topology is a specific word with a specific definition. It's a collection of sets that has to include the empty set and the entire set you're working in, and for us that's the reals. So our collection of sets must contain the empty set and the reals. Any union of things from my collection must be another element of the collection, and any finite intersection of elements of the collection must be an element of the collection. So open subsets obey this. We've already proved the empty set is open. The real numbers on the whole are open. Any union of open sets, whether it be finite or infinite, is open. And any finite intersection of open sets is open. So if I had a collection of all possible open sets, this would be satisfied. The open sets form a topology. And in general, if you're more interested in what are called topological spaces, this is your starting definition, and anything in your topology is what you call an open set. We've gone the other way. We defined open in terms of these little intervals and these epsilons, and observed that it satisfies this condition here. The empty set is one of them. The entire set, the reals, is one of them. Any union of things that are open is open, and any finite intersection of open things is open. But in general, any collection that obeys this is called a topology. You can define other topologies on R. We will finish with a couple little examples, but really, we're just going to work with the standard topology of these open sets based on these epsilons and these little wiggle room distances. So some final results to work on. Here are 4 examples of topologies on the real numbers. The first one only has 2 things in it, the empty set and the reals. The second has all subsets. The third and the fourth are a little more intricately defined, but try to show that they satisfy that definition of being a topology. It contains the empty set, it contains the reals, it has any union of things in the set will make another thing in the set, and any finite intersection of things in the set will make something in the set. But that's really going to finish out this video. A lot of optional topics here, but will be useful later on. So hopefully that wasn't too weird at the end. Hopefully you enjoyed it. Come on back next time. We're going to get back into the real analysis portion and get back to this notion of supremums and infimums of sets.